Capella. Capella is the sixth brightest star in the sky and the third brightest in the Northern Hemisphere. Greetings, friends. This is Dr. Jim Daly for Astronomy for Change. This video and the corresponding article in astronomyforchange.org is the sixth installment in our 10-part series on the 10 brightest stars in the sky. We're going to answer the question, what would happen if we replaced the Sun with Capella, as we did in the previous 5 installments in the series? But first, we have to describe the star and its properties. What would happen to the solar system if we replaced the Sun with the star Capella? Let's find out, but first, let's describe the star and its properties. Capella is a fascinating study in stellar luminosities and evolution. Why? It's a quadruple star system, 43 light-years distant, consisting of 2 binary systems, Capella A, consisting of Capella AA and AB, and Capella H and L. The first binary pair consists of a K0 yellow-orange giant, and the second, Capella AB, a G1 yellow giant. They're separated by 0.05 arc seconds, very small distance on the sky, and that's the actual resolving power of the Hubble Space Telescope. These stars are thus characterized as spectroscopic binaries. That is, you need what's known as an optical interferometer to resolve them. As of now, there is no optical telescope, conventional optical telescope, orbiting or otherwise, with the possible exception of the Hubble Space Telescope, that can resolve this star. Okay, there are certain techniques in optics and optical astronomy where we can use what's known as an optical interferometer. We can synthesize a large telescope by placing 2 smaller telescopes at a great distance separating them. We can synthesize a large telescope by doing that. That's called an optical interferometer, and that's the only way we've been able to resolve the star and know that there are 2 actual stars there instead of just 1. Okay, so the integrated spectral type of these 2 giant stars is a G3 yellow giant. It should be pointed out here that the Sun is a G2 main sequence star. Okay, a G3 star or a G1 star is in the same color temperature more or less as the Sun. So its photospheric temperature, its surface temperature, and the stars don't have a solid surface, by the way. That's very similar to the Sun in terms of color and temperature. The combined light of this spectroscopic binary is what we see in the night sky as Capella, and it is this star that we will use in our hypothetical simulation. Capella AA is the K0 giant star at 2.6 times the mass of the Sun, 8.8 times its radius, and 73 times its luminosity. Well, why is the luminosity so much greater? Well, you look at its radius. It's 8.8 times the radius of the Sun. This star is not a main sequence star anymore. It has evolved off the main sequence and is now burning helium in its core. It has evolved. It's a giant star. The Sun will someday become a giant star, a red giant star. Okay, because it's already cooler to begin with. These 2 stars, were already more luminous and powerful than the Sun when they were on the main sequence. They were similar to star Sirius A, the brightest star in the sky, or perhaps Vega. Capella AA is the K03 giant star at 2.6 times the mass of the Sun, 8.8 times its radius, 73 times its luminosity. Capella AB is the G1 giant star at 2.5 times the mass of the Sun, 12 times its radius, and 79 times its luminosity. Since they're both classified as giants now, we mentioned they've evolved off the main sequence and now burning helium in their cores. This quadruple system makes for a great lesson in stellar luminosity and evolution. One pair has already aged off the main sequence to become twin giants, while the other pair remains on the main sequence and will remain so long after the twin giants are gone. Based on the similarity of their respective masses and their tight orbit, they most likely form together, Capella AA and AB. Conversely, it is highly unlikely that they ever had a system of planets. They are an orbiting binary pair, separated by less than 1 astronomical unit, less than the distance between the Earth and the Sun, 0.74 AU. That distance would have precluded the formation of a stable planetary system. So what's next? They will continue to evolve and expand, reducing their separation and current 104-day orbital period, with the more massive Capella A evolving and expanding somewhat more quickly than its slightly less massive companion. As they continue to expand, bringing them ever closer to each other, mass exchange or transfer may occur, further complicating their evolution. Their estimated age right now is between 590 and 650 million years, and based on their masses, they most likely evolved off the main sequence less than 100 million years ago. The revolution will now quicken, with the current helium-burning phase ending soon, followed by carbon burning. Possible supernova? Not likely. A supernova is probably not in their future. Individually or combined, they lack the minimum 8 solar masses necessary for a Type II core collapse supernova. What is possible, however, albeit unlikely, is a situation where either star, most likely the more massive companion, evolves to become a white dwarf first, and then accretes material off the remaining companion. When the white dwarf star reaches the Chandrasekhar limit of 1.38 solar masses, a Type 1a supernova could result. This is the view of the twin giants, Capella AA and Capella AB, as seen from the distance of Jupiter, 5 astronomical units. It'd be brilliant in the sky, even at Jupiter's distance. We're zooming in towards the 1.5 astronomical units now. This is what they would look like from the distance of the Earth. 1 astronomical unit. They would be brilliant in our sky. They would be scorching the Earth. The two of them. With an apparent magnitude of minus 31.3. Almost 5 magnitudes brighter than the Sun, as seen from the Earth. We would be receiving over 100 times the radiant energy we receive today from the Sun. Difference of almost 5 magnitudes is equivalent to 100 times the radiant energy. It basically would fry the Earth, these twin stars, as seen from the distance of the Earth. At a distance of 5 astronomical units, Capella AB presents with a magnitude of minus 27.9, which is almost 2 magnitudes brighter than the Sun is at the distance of the Earth. And the Sun is minus 26.7 in our skies. That's almost 2 magnitudes brighter at the distance of Jupiter than the Sun is at the Earth's distance of 1 astronomical unit. Jupiter's 5 astronomical units. The second binary pair consists of 2 red dwarf stars, one slightly more massive and luminous than the other. They are separated from the twin giant binary system by 10,000 astronomical units and from each other by 48 astronomical units. The first, the brightest, Capella H, is an M2.5 main sequence red dwarf star with a mass of 0.35 solar, so it's 35% the Sun's mass, with an apparent visual magnitude of 10.2. Basically, you need a large pair of binoculars or an amateur telescope to see it. Right, magnitude 10.2. Just for the sake of reference, the unhated visual threshold for the human eye is magnitude 6.3 under excellent conditions, clear, dark sky, and so forth. Its companion, the star's companion, Capella L, is a fainter M4 main sequence star with a mass of 1/10 the mass of the Sun, which is close to the hydrogen-burning mass limit of 0.072 solar. So a stellar candidate that's less than 7.2% the mass of the Sun will never have enough mass to initiate hydrogen fusion reactions in its core. It lacks the mass necessary to raise the core temperature hot enough where you can have hydrogen ignition, begin nuclear fusion reactions in its core. Any star below 7.2% the mass of the Sun, that never happens. Okay, so this star at 1/10 the mass of the Sun is very close to that limit. It's a very feeble, very small, faint star. It shines with a visual magnitude of 13.7, which is the visual limit for a 15 centimeter or 6-inch telescope under excellent conditions and a very dark sky. When analyzing these two red dwarf stars, they fit a linear profile well within 1 sigma for mass and luminosity. In other words, they're textbook examples of main sequence red dwarf stars. What does this mean and why does it matter? Red dwarfs' internal dynamics are not the same as more massive stars, more massive, more luminous stars. In terms of energy production and radiative transfer, the entire star is fully convective, unlike stars such as our Sun. What does this mean? Sounds like a lot of astrophysical mumbo-jumbo, but it's not. It needs to be explained. The entire star's mass will be used for energy production, unlike the Sun and more massive stars. More massive stars, such as our Sun, use only the inner 30% of their radius, or the core, which contains 70% of the star's mass, for energy production. In other words, 100% of the star's energy is produced within 30% of its radius, internally in the core. And that volume inside the star contains 70% of its mass. This according to the standard solar model, which is what we use to model stars. This is followed by a radiative zone above the core. Basically, it's a very rarefied, clear region inside the star where the energy is transmitted via radiation. Okay, radiation and convection are not the same thing. Radiation is when you hold your hand near a stove, you can feel the heat coming from the stove. Convection is if you touch it. The heat is convected physically into your finger and you burn yourself. This, above, getting back to the star, this is followed by a radiative zone, a convective zone, above the radiative zone that transfers the energy through convection cycles to the star's photosphere, which is otherwise called the surface. It's not a hard surface. And that in turn is radiated away into space. Inside a red dwarf, all the material inside the star's volume, inside the spherical volume, is available for energy production, hence the term fully convective. So all that material, all the hydrogen, is going to be used for hydrogen burning. And these stars, these tiny, feeble stars, they last hundreds, perhaps thousands of times the lifetime of the Sun. The Sun's productive lifespan is about 10 billion years. These stars live hundreds of billions or perhaps trillions of years, hundreds or thousands of times longer than the Sun, because they're misers. They don't need a lot of fuel to maintain an equilibrium balance between gravity and outward gas pressure. It's important to note that the first binary pair, Capella A, and AB, are evolved 2.6 and 2.4 solar mass stars. Based on the respective masses, they were most likely stars similar to Vega or Sirius A, the brightest star in our sky. So now let's take a look, now that we understand the properties of the star system, the Capella star system, Capella AA and AB, let's take a look at what would happen, understanding everything we understand about it now. What would happen to the solar system and the planets if we replaced the Sun with the twin giant stars Capella AA and AB? Let's take a look. Look at the solar system the way it is now. Everything's in harmony and in balance. The Sun is a one solar mass star. All the planets are in nearly circular orbits. And we know Kepler's laws of orbital motion that all orbits are elliptical, some more elliptical than others. Many of the orbits in our solar system are almost circular, the Earth included. We're going to see what happens to those orbits when we replace the Sun with Capella. The first thing we notice is what happens to the orbits. They will become highly eccentric, most likely due to its twin nature. We have twin giants at the center in orbit around each other. That dynamic, we mentioned previously in this video, that dynamic would preclude the possibility of any stable, harmonious planetary system orbiting such a star. Okay, so you notice that the orbits are highly eccentric. All right, with clear apogees and aphelions and perihelions. The aphelion is the furthest point in the orbit, and the perihelion is the closest point. Every one of those planets, every one of our planets, you can see it. It's highly eccentric with a clearly defined aphelion and perihelion. We're going to select several of the planets and see how the temperature changes. Yes, granted, the luminosity and the energy received will increase dramatically, but let's quantify it. Let's see what temperature changes take place on the surface of at least 4 or 5 of the planets. We're going to do the inner solar system, Mercury, Venus, Earth, and Mars, and we're going to try to get to Jupiter and Saturn. So we're going to select 5 of the planets and see how the temperatures change on those planets. Let's take a look. We selected Mercury. Normally Mercury is the closest planet to the Sun right now. And as it orbits the Sun, notice it swings very quickly as it approaches the Sun and then moves quickly away. Mercury is known by the Greeks as the messenger. Okay, so Mercury is moving very quickly. And look at how the temperature changed dramatically. Now here we have Venus. Venus is 500 degrees Celsius. And it's at its aphelion, the furthest distance. Now it's coming in, approaching its perihelion. Look what's happening. It remains pretty constant, interestingly enough. Next we're going to select the Earth and see what happens with the Earth. Now keep in mind, please bear in mind, 100 degrees Celsius is the boiling point of water. Okay? Next we're going to select the Earth. Resume the animation. We're at almost 600 degrees Celsius, the surface of the Earth. All the oceans have boiled away. There's no life on the planet. It's been sterilized. Okay, Earth is right now at its aphelion, its furthest distance from the Sun. You can see how highly eccentric these orbits are. All of them. This star has completely disrupted the stability and the harmony in the solar system. Look at this. 700, 800, 900 degrees Celsius. Almost 1,000 degrees Celsius. The surface of the Earth. Let that cycle around a couple of times, and then we're selecting Mars next. See what happens with Mars. Now Mars is at about 2.5 astronomical units from the Sun. We're at 1 astronomical unit. Mars is at about 2.5. Okay, and watch what happens to the surface of Mars, how hot it gets. It's 360 degrees Celsius, almost 400 degrees Celsius. And notice how circular, how mildly eccentric the Martian orbit is. It's not very eccentric, and the eccentricity of Mars' orbit right now is very small. The Earth is also very small, and the fact that this big star, this dual giant twin binary, has done this has perturbed the orbits to such an extent that almost all the orbits have been disrupted, but they're all now highly eccentric. I'm going to zoom out a little bit, take a look at it from a different perspective. Zoom out so we can get a better sense of where the outer planets are. Let's select Saturn. Take a look at what's going on with Saturn. Okay, Saturn is 120 degrees Celsius. It's above the boiling point of water at Saturn. Currently, Saturn right now is about minus 200 degrees Celsius, approximately. Now that's 300 degrees increase in temperature at Saturn. Now let's select Jupiter. Let's see what's going on with Jupiter. How is this affecting Jupiter? So Jupiter is 360 degrees Celsius. The outer planets, the change in temperature is not going to be as drastic as it is for the inner planets, because they're already far enough away. But look at how the orbits have changed. All of them are highly eccentric, with the possible exception of Mars. Saturn and Uranus, all the outer planets, the entire solar system has been disrupted with this. To say nothing of the inner planets have basically been baked. That all life is gone on the surface of the Earth at this point. It's all sterilized. The twin orbiting giant stars at the center. Represented in this particular simulation as a single G3 giant star. That's evolved off the main sequence. They're both stars, Capella A and Capella AB, have both evolved off the main sequence and are in the late stages of helium burning and will soon start carbon burning. They'll take the carbon that's being built up right now and use that as the next stage or the next burning cycle as the star evolves and ages. It will keep transitioning to the next heavier element that was the byproduct of the previous burning cycle until it gets to iron. In the case of Capella A and B, it's going to stop pretty more or less with carbon burning. It's not going to exceed carbon burning. It lacks the mass to ignite the next heavy element, the byproduct of the carbon burning, which was magnesium and oxygen. Okay, it might stop burning oxygen, but it's not going to be able to burn magnesium, nuclear fusion with magnesium. It lacks the mass. They both lack the mass to do that. Okay, so that's what happened if we replace the sun with the twin giants Capella A and AB. Of course, this is a hypothetical simulation. This would never happen in nature, but it's interesting to see the astrophysical consequences of what happens when you replace, you make changes like this, and see what happens. It allows you a deeper insight, a better insight into how things work. It's also important to note that what's happened to these planets, our planets, with this simulation, is the way it's going to be when the sun eventually does deplete its complement of hydrogen, transitions to a helium-burning star, and the evolutionary changes that it goes through internally, and that will be manifest outwardly as an expanding subgiant into a giant star, red giant star. These same things will happen in about 5 billion years from now, or before then. In about 1 billion years from now, the Earth will become uninhabitable. With every 100 million years, the luminosity of the sun increases by 1%. So in another 1 billion years, which is 10 times 100 million, the sun's luminosity will have increased 10%. At that point, the oceans will start to boil away, and it just gets worse from there, and there's no recovering from that. Once the sun crosses that Rubicon, there's no way, even though the Earth is a dynamic, self-regulating body, and it's been like this for 4.5 billion years, there's no way to adapt to the ever-increasing luminosity from the sun. We're going to have to move. Wherever life is here, if it doesn't move, will become extinct. The Earth will become sterilized. In about 1.5 billion years from now, the Earth will be an inferno, and it just gets worse. So what you see in this simulation portends of what's to come in 4.5 to 5, another 4 to 5 billion years from now, when the sun ages off the main sequence and starts to evolve towards a red giant star. Eventually a white dwarf and planetary nebula. That's how it winds up. But in the meantime, in the intermediary steps, the sun becomes a subgiant and a red giant star. Okay, so what we've just simulated here, and what this simulation has shown, is what's going to happen with our own planets in 4 and 5 billion years from now.
This is Dr. Jim Daly of Astronomy for Change. May you come to love the stars too fondly to be fearful of the night. And remember, the Earth is a mote of dust floating in a sunbeam. That's reality. Everything else is just marketing. The great philosopher Plato famously said, "Astronomy compels the soul to look upward and leads us from this world to another." Astronomy for Change is a non-profit organization whose mission is to effect a positive change through astronomy and science education. It is our belief that by inspiring and empowering current and future generations to become interested and engaged in astronomy and science, this positive change will be realized.
If you enjoyed this video or found it educational or useful, please consider subscribing to our YouTube channel and sharing the video. These actions on your part are free to do and will help us grow. Also, why not consider supporting us by leaving us a tip or buying us a coffee, or perhaps visiting our Patreon page. Any amount would help and would be most appreciated. All the links and details are in the comments section below. And, as always, thanks for watching.